Last Aussie talk of the day, I'm very happy to introduce Vigleik Angeltveit from ANU, and he's going to be speaking about the Picard group of equivariant stable homotopy theory and the slice spectral sequence.
Well, thanks for that, and thanks to the organizers for giving me the opportunity to talk here. There's going to be some equivariant stable homotopy theory here, so we'll see how that goes. The brief outline of the talk is it sort of divides itself in two parts here. So I will start by saying some things about the Picard group, and then we'll get a good way of grading our calculations for some slice spectral sequences. Okay, so let's start with some setup. So in this talk, G will be a finite group. So some of what I say works for pro-finite groups or compact Lie groups or some other settings, but we'll keep it simple and talk about finite groups. So if we have a finite dimensional real G representation, then we can consider the representation sphere. So we add a point at infinity, and then we have a sphere with some interesting G action. And from that, we get an adjoint pair of functors where suspension V means take the smash product with the V sphere and use the diagonal action, and loops V means take the space of maps from SV to your G space and use the conjugation G action. So these are not quite equivalences, but if we make these invertible, then we get a category of G spectra. So we'll call these genuine G spectra. So there are various ways of constructing such a category, but I won't dwell on that. The important thing is that all these representation spheres have been made invertible, and so we have seen spectra in a few other talks this week, but I think always if there's been a group action, there's always been just a naive group action, and I'm going to insist that we take put the G representations into the story. Okay, so this is a genuine G spectra. Now we have also seen some Picard groups once or twice. So in this setting, we could say that just the Picard group, not I won't do anything more fancy. Here, the Picard group of the category of G spectra is just the isomorphism classes of invertible G spectra under the smash product, which the young people these days call it a tensor product, but I'll call it the smash product. And well, typically when people do equivariant stable homotopy theory, they grade things on the real representation ring, but in some sense, the Picard group is a more natural home for the grading, because if say two representation spheres are equivalent, we shouldn't have a separate homotopy group for each of them. So if we have an invertible G spectrum like a sphere, then we could talk about the homotopy groups, like the ALF homotopy group of that. Okay, so that's sort of a natural thing, and there's immediately we could see that there's a map from the real representation ring to the Picard group that sends a virtual representation to the corresponding sort of virtual representation sphere. And that makes sense now because in G spectra we could well, if we want, we could start with the sphere spectrum and then we could shift it up by V by smashing with the V sphere, and then we could shift it down by W by taking the W loops. You might argue that there are some choices involved here, and you might feel a little bit nervous about that. But for example, Dan Duggar has worked out the sort of coherence theory for this sort of setting. And if you want to grade things on either the real representation ring or on the Picard group, it's possible to make all the right choices to get a coherent theory. Okay, so there's two sort of obvious questions about this this map from the real representation theory, real representation ring to the Picard group. One is it injective? In other words, is it possible to have a S alpha homotopy equivalent to S beta for alpha not equal to beta? Sometimes yes, sometimes no. And is it surjective? In other words, are there more exotic invertible elements, invertible G spectra? Okay, so these are some questions you could ask in this setting. And before I try to answer that question in the specific setting, I'm going to tell you a little bit more about how we sometimes work with these genuine G spectra. So I'm not sure how familiar people are with these sort of things. So I'm going to try to motivate the notion of a Mackey functor here. So to start with, let me just put up the equivariant Whitehead theorem, which says that if we have a map between a sufficiently nice G spectra, like GCW spectra or something like that, then it's a homotopy equivalence if and only if it induces an isomorphism on homotopy groups of fixed points for all subgroups. So, so the moral of this is that we really need the homotopy groups of the fixed point spectra for all the subgroups of G. And we could package these homotopy groups of fixed points in by doing the following. So for every finite G set, we could look at homotopy classes of maps from Sn smashed with the finite G set with a disjoint base point to X. And so, for example, if we start with G mod H, and we look at homotopy classes of maps from some suspension of G mod H to X, that's actually, by an adjunction, this is the H equivariant homotopy class of maps from a sphere to X. And we could like this.
Sorry, can I have a question, please? A stupid question. In your homotopy groups, are all subgroups involved, including G itself?
Yes. So yeah, so for all, so this is for all H less than or equal to H subgroups of G, including G. Absolutely. If you were doing something slightly more general, you would say maybe closed subgroups here, but since we're doing finite groups, we don't need to say anything more about that. Is that okay?
Yeah, it is. Thanks.
Okay, so for each finite G set, we get a sort of a homotopy, kind of a homotopy group after smashing with that finite G set, and this is indeed a functor from the category of finite G sets and G maps, but it's even more because given a map of finite G sets, we get maps in both directions here. So there's a restriction map, which is given just by pre-composing with this map of finite G sets, and then there's a transfer map, which goes in the opposite direction. And we could package this as a Mackey functor. So we get a functor from the category of spans of finite G sets to abelian groups. So a span of finite G sets will look something like this. It's some other finite G set that maps to both S and T. And we think of the map from U to S here as then encoding a restriction map, and the map from U to T as encoding a transfer map. And additive, that just means that M of a disjoint union should be M of S Cartesian product with M of T. So I could say direct sum here, but I'm going to say Cartesian product because if you kind of build this theory, then you start with just a functor from spans of G sets to sets, and then you impose a little bit additional structure to get or you ask, you start with the functor from spans of G sets to just set, and then the fold map from S disjoint union itself to S gives you an addition map, and then you sort of at the last possible minute you ask for inverses there. Okay, and homotopy groups of a G spectrum is each homotopy group of a G spectrum is now, of course, a Mackey functor. And if you want, you could package this information of a Mackey functor as being one abelian group for each subgroup, together with a restriction map for each subgroup K of H, and a transfer map going back. And then there's a little bit extra structure. Like if you have conjugate subgroups, you should get the same abelian, or should get isomorphic abelian groups, and there's a little bit of a group action left there. But we're not going to worry about all of the structure because some of this it won't all be there in the examples. Anyway, so this is the kind of home in which one does algebra. So this is supposed to, so a Mackey functor is the right notion of instead of just talking about abelian groups, we talk about the Mackey functors. And we take a cohomology with coefficients in a Mackey functor rather than coefficients in an abelian group. Okay, so to be very concrete, let's take a cyclic group of order P. Then a Mackey functor consists of there's really two abelian groups, one associated to the trivial group and one associated to the whole group, and then there's a restriction map going down and a transfer map going back up, and then there's an action of G on the bottom. There's let me just give a few examples of Mackey functors that you might see. You could, for example, take like fixed an abelian group and just put that abelian group in every spot and say that all the restriction maps are the identity and all the transfer maps are multiplication by the index in your group of the subgroup. Or you could do it the other way and say that all the transfer maps are the identity and the restriction maps are multiplication by the index. Or you could make a Mackey functor that's trivial at the bottom and your abelian group at the top level. So those are some things you could do. Another thing you could do is the okay, so we call this maybe the constant Mackey functor, and I don't know, co-constant Mackey functor. I don't know if the last one has a standard name. The Burnside Mackey functor is an important Mackey functor because it's pi0 of the sphere spectrum, and it's at the top level. It is it's the group completion of let's say finite G sets under disjoint union. So here 1z would be represented by G mod G, and the other one would be represented by G mod E. This restriction map forgets the G action and just counts the cardinality, and then there's a transfer map that like taking Cartesian product with G. Now, another thing we could say about this Burnside Mackey functor is that this is the unit for a symmetric monoidal structure on the category of Mackey functors. So this symmetric monoidal structure, it's a bit like the tensor product, but you don't just take the tensor product level wise. There's a little bit more going on there, but we won't, let me not dwell on the details of the construction of that either. Instead, let me put up a theorem. So if we consider just a cyclic group, a cyclic group of order n, then this map takes a real representation to the corresponding representation sphere, is indeed surjective. So there are no exotic invertible elements in this case. And you could calculate exactly what this Picard group is. So it's this first factor here, that comes from the Picard group of the category of Mackey functors. So you can talk about invertible Mackey functors as well and compute the Picard group of that. And this other factor here, it's kind of a dimension. So if you started with a real representation, say virtual real representation, it has a dimension function that sends a subgroup to it sends a subgroup H to the virtual dimension of the H fixed points. And you could do something similar with an invertible G spectrum. Okay. So one remark here is that Ayala, Mazelke, and Rosenblum have the same result for a prime power cyclic group at an odd prime. So so they put that on the archive a few months ago, and I haven't fully digested the paper yet because I just found it, but they appear to use different techniques. There's some infinity category there that I don't quite understand yet. Anyway, so I'm not going to say too much of the proof, but part of the proof involves computing the pi zero of one of these representation spheres. So if you have one of these representation spheres of dimension 0, you could talk about you could compute the pi 0 of that, and then that is going to be yeah. What about injectivity? So right, so it is not going to be injective because well, it depends on n. If n is 2 or 3, maybe it's injective, but it's not going to be injective in general because this real representation ring, it's bigger than this this Picard group, right? Like if n is large, you have many more real representations than you have z summands here. So it's not going to be injective in general, but because I forgot to say that. So yeah, if you have one of these representation spheres of dimension 0, like dimension 0 on all the fixed points, then sort of by abstract nonsense, pi 0 as a Mackey functor is going to be invertible, and it is just possible to explicitly compute this. And so, for example, if you take a cyclic group of just order p, then to make that so that the Burnside Mackey functor looks similar. Then then if you let say lambda a denote the usual representation of G, where with the sort of usual sped up action, then S lambda 1 minus lambda a is one of these virtual dimension 0. All right, so I see I wasn't quite precise here in my remark. You need to combine one of the theorems of Ayala, Mazel v. Rosenblum with the theorem of Krause to see that their calculation actually is a calculation of the Picard group of G spectra. Okay, so if we'll look at one of these virtual dimension 0 representation spheres, you could compute pi 0 as a Mackey functor, and it comes out to be almost the Burnside Mackey functor, but it's a kind of a little bit twisted up. The structure, the restriction map for this Burnside Mackey functor is almost the same as the restriction map for, or the restriction map for this Mackey functor is almost the same as the Burnside Mackey functor, except we have a multiplication by a instead of a 1 in one place. And well, you could be so I'm not going to be very explicit in this talk, but you can be very explicit and give everything inside here a GCW structure, like a GCW spectrum structure, and really get your hands dirty with the calculations here. And so this involves sort of a few small spectral sequences. They're kind of the spectral sequence of a little double complex, but you know, you have to take some product GCW structures, and I think trying to do that in a talk is maybe not going to work. Okay. Now, one thing that you could compare this to is if you look at just Z modules. So just look at modules over the constant Z Mackey functor. Then if you do the corresponding calculation, the Picard group is trivial. And from that, you can see that if you start with one of these virtual dimension 0 representation spheres, or the, yeah, and you tensor with the constant Z Mackey functor, then the twist disappears. So this sort of twisting, it disappears. And the upshot is that if you want to compute, say, homology or cohomology with a constant Z coefficients, or there's, you know, slightly more generally with coefficients in any cohomological Mackey functor, then this extra twist, it goes away. And so homology and cohomology, they don't see this torsion part of the Picard group. And so returning to this example of just a cyclic group of order P, it gives you some simplification. So usually people would do these calculations graded on the real representation ring. So that's the usual grading in the literature that people use, but we could grade it on the Picard group instead, and then that's much smaller. And if we're doing ordinary, like, say, homology, then this little torsion group also disappears, and we're left with just a Z cross Z grading. Okay, so that was part one. Now I'm going to try to say something about the slice spectral sequence as well. And you know, this conference is supposed to be hidden motives. So the slice spectral sequence is inspired by a spectral sequence from that's computes algebraic K theory from motivic cohomology. And then Dan Duggar took this and made it into a spectral sequence for C2 equivariant complex K theory, by which I mean really a real K theory. And I included a picture that I cropped from his paper, where you could kind of see how you get the like usual real K theory from this. Now Hill, Hopkins, and Ravenel took this and they generalized it to a version that works for any finite group. And then they used it with great success for the cyclic group of order 8 to solve the Equivariant variant 1 problem. Okay. Now, before I say exactly what this slice spectral sequence is, let's talk about the cohomology of a point. And let's talk about it just for the group C2. So I've drawn a picture of the cohomology of a point here. So there are various Mackey functors involved. There's the constant Mackey functor, which is in red here. There's the co-constant Mackey functor in green, and then there's one that's just an F2 on the bottom in blue, and an F2 at the top in black. And you can see there's a kind of there's a positive cone here on top, and this is the same positive cone as you see in the motivic cohomology of a point. And then in topology, but not in the motivic world, we also have this negative cone here. So this is kind of what the cohomology of a point looks like. I mean, saying cohomology of a point, it sounds kind of silly, right? So cohomology of a point should be trivial, but it's really, it has to do with all the virtual representation spheres. Okay, so now if you try to draw this picture with an ROCP grading, you'll have a hard time drawing it, right? Because you have sort of many different axes. But if you do the Z cross Z grading, then the picture for an odd prime is going to be very similar to the two. Okay, so let me try to briefly say what this slice spectral sequence is supposed to be. So, so it's in a sense it's an equivariant generalization of the Postnikov tower. So when you build a Postnikov tower, Pn of x is you get that from x by insisting that you have no non-trivial maps from spheres of dimension higher than n. And equivariantly, we want to take the regular representation seriously. So we want to say that we don't have any maps from the representation sphere of for a number of copies of the regular representation when that number of copies of the regular representation has dimension greater than n, and we include the regular representation of subgroups induced up to G. So this gives the slice tower.
Excuse me, subgroups including G itself again.
Including G itself. Yep.
Thanks.
Always including G itself. So this gives an analog of the Postnikov tower, but somehow a more interesting analog in some sense. And you could kind of let me zoom out a little bit here. You could put the slice tower. I drew the slice tower here vertically, and then I drew the co-slice tower horizontally. The co-slice tower is analogous to the Whitehead tower. And you could fill out this diagram with, you could either take homotopy fibers of the various vertical maps, or you could take homotopy co-fibers of the various horizontal maps. And the slice spectral sequence, you could say it's either the spectral sequence that's associated to this vertical tower, the slice tower, or associated to the horizontal tower, this co-slice tower. like they both give the same spectral sequence. Oh, I have an example here. Let me not dwell on this example too much. Other we take the Elmer-McLean spectrum for the constant Mackey functor on F2, and I took some suspension of it. I just want to show you sort of a little bit how this looks like, and oops, that's not right. And what kind of things happen. So in this example, there are some differentials. So the E2 page looks like that, and then after that, the kernel, like those black dots go away, and the kernel of that long differential is one of these blue ones, and then there's a black dot, and then there's an extension that makes this into one of these green ones. So let me not dwell on this example, but just to show you that these are kind of things that happen in the slice spectral sequence in a kind of simple example. So this was the E infinity page here. Now, if we take any abelian group and we continue to look at the cyclic group, with G be the cyclic group of order P, and then take any abelian group, we could take we could consider a map from the co-constant Mackey functor to the constant Mackey functor that it's just multiplication by P at the top level and the identity at the bottom level, and this has a kernel and a co-kernel. So it's the sort of P torsion points of A and the A quotient by P. And now we could take an arbitrary representation, and I'm going to say, instead of really thinking about the whole real representation ring, we'll pretend that the real representation ring of CP is just as an abelian group. It's a free abelian group on the trivial representation and a single two-dimensional representation, because after we take homology, that's all we can see anyway. And so then we get to pretend that the regular representation is 1 plus P minus 1 over 2 copies of this two-dimensional representation lambda. And if P was 2, the signed representation is half of lambda. And so I'm just going to put this up here, that there's a uniform way of always describing the slice spectral sequence in this situation. So we have here our group is the cyclic group of order P, so for any prime P. And if we take the constant A Mackey functor and we suspend it by any virtual suspension, then it's possible to say exactly what happens in the slice spectral sequence. And it really divides into 3 different cases. So this R, it kind of says it measures how far V is from a multiple of the regular representation. And so if R is pretty close to the regular representation, then the slice spectral sequence doesn't do anything. If R is greater than 2p, then this, you could say the slice tower has a certain specific form, and all of the fibers are given by these Allenberg-MacLane suspension of this Allenberg-MacLane spectrum of this Mackey functor that has the p torsion points of A at the top level and 0 at the bottom, or the other one that has the A quotient by p at the top and 0 at the bottom. And if R is less than 0, then it's not so easy to describe the slice tower, but you can describe the co-slice tower. And again, now the co-fibers here are going to have the same form. And I didn't put this in the slide, but it's possible to say exactly what each of these xi's are as well. And it's possible to say exactly what the differentials and extensions in these spectral sequences do. So there's been some calculations like this in the literature, and I don't have a list. I don't have a list right here, so let me not try to make a list. But there's been sort of various calculations, calculations for p equals 2, and maybe just for certain suspensions, maybe trivial suspensions, and for certain coefficients like F2 coefficients or constant Z coefficients, and then a few scattered other calculations, but nothing very systematic. So I kind of felt like somebody should write down in a systematic way what happens here. And I think that's exactly my time. And so I will stop here.
Thank you very much, Vigleik.